Hi, I'm Daniel Perez. I'm a PhD student at Imperial College London. And today I'm going to present a broken meter, attacking resource metering in EVM, which is a joint work with my supervisor, Benjamin Lifshitz. And basically what we do here is we worked on a DOS attack against the way that Ethereum does its metering, so using gas. So if I, here we go. So I'll start with a bit of background, especially about smart contracts and this metering. So first, well, smart contracts, I think a lot of you probably already know, but I'll go quickly through it. So there are programs which are meant to be deployed on the Ethereum blockchain for these Ethereum smart contracts. They're typically written in a high-level programming language, Solidity for Ethereum, then compiled into a bytecode representation, which is meant to be run on the Ethereum virtual machine. Then they are deployed on the Ethereum blockchain using a transaction. And once they're deployed, they get their address, and people can interact with these contracts by sending transactions to this address. And then contracts can interact with other contracts and do computations and whatnot. So here there's a very important part, which is given that this needs to be executed on every single node on the network, there need to be some limitations on what people can execute or not. Because if you had, for example, an infinite loop, it would just like block the whole network. So to work around this, how it works in Ethereum is that they have this notion of gas, which is basically a cost which is assigned to each instruction. And when an instruction is executed, it will cost a certain amount of gas. So summing up all the cost of each instruction and adding like a fixed fee for each transaction execution, we get the total cost of the transaction, of the program for this transaction. And if the program runs out of gas, so if the amount of gas consumed goes over the budget, then there's an out of gas exception which is raised and the execution stops. So that's more or less how it is limited. And another important point here is that the person sending the transaction will be in charge of paying the fees. So this fee will be basically this gas cost multiplied by the gas price, which is basically the amount of ETH, or the amount of money that the sender is ready to pay per unit of gas. And this is very important because this is how basically Ethereum prevents people to try to spam the network, because it costs money to actually do this. And in a perfect world, this would actually prevent all attackers to try to DOS the network. But obviously, this is quite hard to get perfectly right. And in the past, there had been a couple of instances of attack against this metering mechanism, so this gas mechanism. And I think both of these were in 2016, if I remember correctly. And both were basically had the same root problem, which was that some of these instructions were underpriced, and an attacker could spam the network using this instruction and make it very slow. So for example, for the Xcode size, this is an instruction which tries to read the size of a smart contract stored on the blockchain. And it requires, therefore, the node to perform I/O access, to read from the state. Well, reading from the state is not free, and it's often, so it's quite I/O heavy as an instruction, but it was very cheap to execute at the time of the attack. And so basically what an attacker could do is just spam the network with this Xcode size, and this would make everything very slow. So this had been fixed by simply increasing the cost of this Xcode size instruction by an order of magnitude. And then it became so too expensive to try to perform such an attack. And this suicide attack, I won't go into too much details, but it was basically the same overall idea, which was that instructions were underpriced. So what we wanted to see was if, is it all fixed, or there are still some problems with this metering, and can we still attack this? What we first did is we did some empirical analysis on the actual transactions executed on the Ethereum blockchain, and try to see how this correlates with different resources, with memory, with CPU. So we forked the C++ client of Ethereum, which is called Alice. And we instrumented the CPU, the memory, recorded all this, and replayed the Ethereum blockchain transactions for a couple of months. So while doing this analysis, first we try to see basically what resource correlates the most with the gas usage. And well, as the gas is designed right now, it's mostly everything which is related to the state, so reading from the state and storing in the state, which is even more expensive, which was supposed to be the most correlated. And this is actually what we got as a result, as the correlation if we see memory, CPU here, which is basically the clock time, and storage, which is the amount of, the number of times or that a program reads or writes into storage. Here, clearly, storage is dominating this. And then we try to aggregate different metrics. So we try to aggregate storage and memory, and we see that this actually increases the correlation, which is what we expected. But one thing we did not really expect here is that if we try to add the CPU, so the clock time, into this correlation, then the correlation decreases. So basically that shows us that, well, there are probably some programs which are quite slow, but that doesn't really increase the gas cost or the price that the person sending the transaction needs to pay. So next, we tried to see more or less where this was used. And this was mostly used in instructions with a very high variance in terms of execution time. So we see that most of these transactions, instructions with a high execution time try to read from the state at some point to look at something in the state. So for example, balance tries to get the current balance of an account. And this requires obviously to read from the state, so it's fairly IO intensive. And same for sload and for xcode size. The other two instructions are a bit less interesting because they depend mostly, the execution time depends mostly on their arguments, so this is not very important for the rest. But here's the important thing is to see that everything that we read from the state has a fairly high variance here. And so obviously for this kind of thing, this variance mostly comes from caching, so we wanted to see more or less what was the effect of this caching. And what we did here is we looked at the page cache, and we generated some random contracts and executed them with and without this cache. And we saw that on average, the program's execution time was improved by 28 times with the cache available. And obviously, this is modeled nowhere in this gas pricing. So, the main idea here was to see, can we basically exploit this and try to create some contracts which will always result into cache misses, and so to do this, we want to do this in a fairly systematic way. So we designed what we call the Resource Exhaustion Attack. So basically what we try to do here is to find programs which minimize throughput, where here throughput is defined in terms of the amount of gas per second that the EVM is able to execute. So this can be fairly easily expressed as a search problem. We have our search space here, which is the set of valid programs. Here, for a program to be valid, it needs to be able to be executed by the EVM. So there are a couple of properties. For example, the number of elements of the stack and a few things that we'll talk about. Then there is a function to optimize here, which is our throughput. We want to minimize this. And finally, we have a gas budget, which is a fairly simple constraint to fulfill. So obviously here, as our search space is a set of valid programs, is way too big to be explored fully. So we designed a genetic algorithm to try to find these very slow contracts and to optimize and solve this search problem. So our generated contracts here, as the search space was already very big, what we wanted to do was to design our algorithm so that every single program generated is always valid. So as I quickly mentioned before, there are a couple of constraints which need to be taken care of, as the state of the stack, the memory accesses, the stack of, and so we want to do this, of course, when we create the program, but also when we do the crossover and mutation, so when we generate new programs from existing programs. So details here in the paper. I won't talk too much about this right now. And finally, another restriction that we put here, because it's not very relevant to throughput, is we just left out all the loops because it makes program generation more complicated without really bringing anything to the table for this particular problem. And then another fairly important constraint here is that our search space is very big. So here we want to have fairly good initialization values so that our algorithm can converge in a fairly reasonable amount of time. So here what we did to find this initialization values is we reuse the measurements from our empirical analysis. During our empirical analysis, we mostly have, for each instruction, the average clock time that it used, and we know each time how much gas it's consumed, so we can compute the average throughput for each instruction. And then we designed our program initialization such that when we sample the instruction to create a program, we assign a much higher probability to instructions which have a slow throughput than one which have a higher throughput. So, but we didn't want to exclude completely the one with higher throughput to be sure that we don't miss some combination which could work out fairly well. So we use this kind of probabilistic approach to find some OK initialization values. So given all this, we ran our experiments. Yeah, here it is. And so when running this genetic algorithm, we saw that first our initialization values seem pretty good, as we got an average of 3 million gas per second on the first generation, which is compared to the average program run on the exact same machine when replaying the blockchain transactions. It was 20 million gas per second, so we're already 6 to 7 times slower than just the average program. Then we can see that it decreases fairly quickly to 500,000 gas per second. And finally, at generation 200, it plateaus at 100,000 gas per second. So to give an idea of how bad this 100,000 gas per second is, it's 200 times slower than the average contract. So this is really, really slow. And so given this, so we thought a bit about like how this could be a problem and about the kind of implication of such programs. And well, implication-wise, basically, this would mean that at this rate, a lot of nodes at least, would not be able to keep up the pace, the block production pace, so would just get out of sync. And also, this could very likely result, as it resulted in previous attacks, in a decreased throughput and a decreased block production rate. And the next important point here is in terms of cost and of feasibility. So this is actually super cheap to execute. So to just keep nodes out of sync, as the rate we saw just before, we would need to include 2 million gas worth of malicious transactions per block. And at the current price of Ethereum and the gas price, this would be around $0.7 to keep the nodes out of sync for one block. So it's less than $1 per block to actually perform such an attack, which is really, really cheap. And so, well, who would like to do such a thing? There are a couple of potential attackers for such an attack. First, the miners, because they have a double incentive here, trying to, well, main incentive being trying to keep the other miners a bit behind in terms of competition. If they can get a head start for mining the next blocks, this gives them financial incentive. And they can also include this kind of transactions for free because they decide of their own gas price. So they have a clear financial incentive to do such a thing. And there are also obviously like the parties hostile to Ethereum and other blockchains. As we have already seen in the past, some blockchains have tried to attack Ethereum. So this could also be potential attackers here. And finally, for some limitations, because this is obviously not perfect, well, we are not sure exactly what kind of hardware the full nodes usually run. And this is typically works much better, obviously, on commodity hardware. So it's hard to have an estimate of how many nodes would actually be very impacted by this. But nevertheless, so we wanted to see if this attack would work only on our C++ client, or if it would work on the other clients. So we run our contracts on the two major clients, so Guess and Parity. And so what we looked at here is the amount of time it would take to run a full block filled with these malicious transactions. And obviously, the client on which we optimized, so the C++ client, was the slowest one, with 93 seconds for a single block to execute this whole block. But even for Parity, which was the fastest of the three, it took 47 seconds to execute all this. So given that a block is produced every 13 seconds in Ethereum, the node would never be able to keep the pace if the network were to be under attack. So as we run this on a cloud server with a fairly commodity hardware setup, we also tried to repeat the experiment with the fastest of the 3 clients, so parity, on a much more powerful bare metal server. And even then, the time was around 18 seconds to execute this block, so this would still be very slow and too slow to keep up. So as this was quite bad, we decided to contact the Ethereum Foundation, and we submitted a bug bounty, and then spoke to the Ethereum developers, and they came up with a patch which improved the situation vastly. And currently on the mainnet, so the new version is fixed, and now it can run the exact same transactions in only a bit more than 3 seconds. So in the current state now, it's mostly fixed and it's fast enough to work even under attack. And so finally, what has been deployed right now is mostly a short-term fix. So here there are a couple of fixes which we can think about to improve the situation. But mostly for short-term fixes, it's really improving the throughput of this I/O instructions. So either, as we have seen in the past, increasing the cost of the I/O operations, either using some smart data structures or caching strategies to try to improve the speed of these instructions. But on the longer term, there are quite a few different things that the Ethereum team is working on, and there's been a lot of research on. So for example, one is stateless clients, where basically the transactions are received with the data needed to execute them, and also with a proof that this is correct. And this would indeed completely solve the problem, as this I/O access would be almost inexistent. And there is also sharding, which would a bit reduce this state bloat, and which is another potential improvement to this issue. So this is pretty much it. I just want to thank Matthias Egli and Hubert Riesdorf from PwC Switzerland, who helped a lot with the disclosure and with all the experiments. And yes, that's all I have to say for today. Thank you.
Thank you. We have time for one quick question. So maybe I'll start probably something comes up. So I didn't get the motivation for the generic algorithm. Is it a standard technique towards moving?
Well, basically the idea was trying to find programs with lowest possible throughput. So it's kind of an optimization problem. To solve it, we chose a genetic algorithm because it's quite easy to combine and to mutate and to basically create new programs. So it fitted quite well the task we had to solve. This is the main reason why we did this.